Hey folks, Bill Armstrong here. This is the Week 9 preview video. In Week 9 you're going to see and learn things such as synthetic division, the Remainder Theorem, Factor Theorem, zeros of a polynomial, fundamental theorem of algebra, and then you'll end the week looking at rational functions and their graphs. One of the first things you'll see this week when reading the text will be synthetic division. And I assume most of you have already seen synthetic division, but I thought I'd do a quick example just to review the process of synthetic division. So, if you're given the function 2x to the fourth plus a 3x cubed minus a 4x squared plus x minus 2, and this is divided by x minus 2. The process of synthetic division is really taking the long division and just condensing it down so it's not quite so cumbersome. And then here is the process to do this. This is the process of synthetic division. You write down all the coefficients of the function that you are going to divide. So you write down the 2, 3, negative 4, 1, and negative 2. And then I make a structure like this. I have to leave space here because numbers are going to go in here. And then I write down what I'm dividing by. Well, I'm dividing by x minus 2. In general, the form is, like an x minus c, but the number I'm interested in here is 2. If this were x plus 2, I would have a negative 2 out here. And now here's the process of synthetic division. You just start off, it's pretty straightforward. This 2, you just bring it on down here and write the 2. And now the process, you take this number times this number, so 2 times 2 is 4, and you put the 4 right there. Add 3 and 4, well that's 7. Now you repeat the process. 2 times 7 is 14, so you put a 14 here and add. Get 10. Repeat the process. 2 times 10 is 20. So put 20 under the 1 and add. You get 21. Then finally 2 times 21 is 42. So you put a 42 here and you add and you get a 40. So here's what you have. These numbers here are the coefficients of the quotient. The 40 is the remainder. So that means you could write down the quotient, if you will. When you take 2x to the fourth plus 3x cubed minus 4x squared plus x minus 2, and you divide it by x minus 2, you could write down that the quotient, and I'll write that as q of x, is 2, and then the variable is x, and the degree is 1 less than what the degree of our polynomial was, our dividend. So 2x, 1 less than a 4 is a 3. So 2x cubed plus 7x squared plus a 10x plus a 21. And then the remainder, this is the remainder. It has a remainder of 40. Another thing that you could do, and this is kind of the cool part, if you will, you could take the original polynomial and you can now write it as x minus 2, that's the divisor. So you could take the original polynomial and write it as x minus 2 times the quotient, 2x cubed plus a 7x squared plus a 10x plus a 21, then plus the remainder. So the general form is you can take the original function and write it as the divisor times the quotient plus the remainder. Now that's a quick review of how to do the process known as synthetic division. Alright, hey, next up is the remainder theorem. I've written down the remainder theorem, or an abbreviated version of the remainder theorem. The remainder theorem basically says if you take any polynomial function that I generically call f of x, and you divide it by an x minus c, that if you go through the division, you're going to get a remainder of f of c. So what that means is that, if you look at the last example we did, we took the polynomial function 2x to the fourth plus 3x cubed minus 4x squared plus x minus 2, and we divided it by x minus 2. If we take that polynomial function and we evaluate it at 2, we do f of 2, we would end up with 40, which was the remainder. Let's try another example. Let's say I'm going to take the polynomial and I want to know what is the remainder when the polynomial function x to the fourth plus x cubed minus 21x squared minus x plus 20, when this polynomial is divided by x plus 5. Well, I suppose we could take this mess and we could crank it through the process of synthetic division. But if we just want to know the remainder theorem tells us how to do that very, very quickly. So here, we're taking this polynomial and we're dividing it by x plus 5. Notice the remainder theorem says when you take a polynomial and you divide it by x minus c, there will be a remainder of f of c. So if I want to consider this when I'm dividing it by x plus 5 to be of the form x minus c, if I want to write this in an x minus form, let me get out the brown chalk here, x plus 5, that has the form of x minus negative 5. So to determine the remainder, all I have to do is evaluate the function at negative 5. So I just compute the f of negative 5. So that's a negative 5 to the fourth plus a negative 5 cubed minus 21 times negative 5 squared minus a negative 5 plus 20. And see, I cranked this through my calculator earlier, and all of this stuff ends up giving a result of 0. So when I take this polynomial and I divide it by x plus 5, I get a remainder of 0. Hey, if I get a remainder of 0, that means x plus 5, what it means is x plus 5 is a factor of this big ugly polynomial, which is kind of cool. I now know a factor. And that transitions us into the next topic, which is the factor theorem. So here we are talking about the factor theorem. And all the factor theorem really says, in an abbreviated version, is x minus c is a factor of a polynomial f of x if and only if f of c is 0. If and only if means that it's a two-way street. It means x minus c is a factor of the polynomial f of x, then f of c is 0. It also means if f of c is 0, then you know x minus c is a factor. So see, the remainder theorem can have some power when combined with this factor theorem. If you use the remainder theorem, the last example that we just did, if you use the remainder theorem and you get a remainder of 0, then you know you have a factor. So that's where the power comes here. So I would say, just to kind of remember that, if when you use the remainder theorem and you get a remainder of 0, you then know you have found a factor. So let's do a quick example. Suppose I want to know, is x minus 2 a factor of the function x to the fourth plus an x cubed minus 21x squared minus x plus 20. Well, the quick way I'm going to determine this is I'm going to just quickly use the remainder theorem. I'm going to use the remainder theorem, and if I do f of 2, remember x minus c, so we have c as a value of 2. If I evaluate the function at 2, that's going to tell me what the remainder is. If the remainder is 0, then x minus 2 is a factor. If the remainder is, if we get a result of not 0, therefore the remainder would not be 0, then that is not a factor. That's how straightforward it is. So let's go ahead and let's evaluate the function at 2. Keep in mind, the general form is x minus c. So x minus 2, c has a value of 2. So we toss 2 in for the x's. And if I crank this through my calculator correctly, to 2 to the fourth plus 2 cubed, etc., I end up with f of 2 being negative 42. That is not 0. Since it is not 0, that tells me that x minus 2 is not a factor. And that's all there is to that. Okay, the next topic you'll see this week is a theorem called the rational zeros theorem. I've written a very abbreviated form of the rational zeros theorem, and what I've written down basically says P over Q is a rational zero. It'll be a rational zero of a polynomial function, where it's important that we note P over Q has been reduced to lowest terms, where P is a factor of the constant term and Q is a factor of the leading coefficient. So what the rational zeros theorem really does is say, hey, you look at your polynomial, you list all the factors of the constant term, you list all the factors of the leading coefficient, you make this fraction out of those factors, list them all, and if the polynomial has a rational zero, it'll be in the list that you have written down. Let's do a quick example to show you what I mean. Let's just simply list all of the possible rational zeros of the polynomial 4x to the fourth plus x cubed minus 40x squared plus 38x plus 12. So here are the key parts. This is the leading coefficient, so that's going to match up with the Q. Way down here is the constant term. That's the P. So how I do this is I just list the factors. So I list the factors of P. I'll start with P, since P over Q, I'll start with P first. So the factors of P, now let's look at the number 12 and let's think of all the factors of 12. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Those are all the factors of P, all the factors of the constant term 12. Now let's list the factors of the leading coefficient, Q. Factors of 4, plus or minus 1, plus or minus 2, plus or minus 4. So when we write down the list of all the possible rational zeros of this polynomial function, the possible rational zeros, I'm just going to make all the fractions that would come out by doing factors of p over factors of q. So plus or minus 1 over plus or minus 1. Well, that's plus or minus 1. Plus or minus 1 over plus or minus 2. Well, that's plus or minus 1 over 2. Plus or minus 1 over plus or minus 4. That's plus or minus 1/4. Keep moving on. Plus or minus 2 over plus or minus 1. Well, that's plus or minus 2. Plus or minus 2 over plus or minus 2. Well, that would reduce down to 2 over 2 is 1, plus or minus 1. I already have those listed, so I don't have to list them again. Plus or minus 2 over plus or minus 4. Well, that would reduce down to 1/2, so plus or minus 1/2. Hey, I already have those listed, so I don't have to list them again. I move to the next factor of p. Plus or minus 3 over plus or minus 1. That's plus or minus 3. Plus or minus 3 over plus or minus 2. That's plus or minus 3/2. Then plus or minus 3 over plus or minus 4 is plus or minus 3/4. Move to the next one. Plus or minus 4 over plus or minus 1, that's plus or minus 4. Plus or minus 4 over plus or minus 2, that would reduce down to plus or minus 2. I already have it listed, I don't need to list it again. And finally, plus or minus 4 over plus or minus 4 would reduce to plus or minus 1. And I have that listed, so I don't have to list it again. So I move to the 6. Plus or minus 6 over plus or minus 1 is plus or minus 6. Plus or minus 6 over plus or minus 2, that would reduce to plus or minus 3. I already have it listed. Don't need to list it again. Plus or minus 6 over plus or minus 4, that would reduce to plus or minus 3/2. And I already have it listed, so I don't have to list it again. Move to the last one, plus or minus 12 over plus or minus 1. So that gives me plus or minus 12. Plus or minus 12 over plus or minus 2, that's plus or minus 6. I have it. And plus or minus 12 over plus or minus 4 is plus or minus 3, and I have it. So this list here, good grief, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Counting plus or minus, there are 20 possible rational zeros for this polynomial function. To put it another way, if this rational function has a rational zero, it's in this list. We have it in the list somewhere. So now the game is going to be, what are the actual rational zeros? We just know the possible rational zeros. And that's going to lead into a quick discussion on the fundamental theorem of algebra. All right, hey folks, I'm not going to write this down. You can read it in your e-text about the fundamental theorem of algebra. In short, the fundamental theorem of algebra says every polynomial function of degree n, which is greater than or equal to 1, has to have at least one complex zero. Another way to phrase that, I kind of turn it around a little bit, and I'll write this down. A polynomial of degree n, so if you have a polynomial of degree n, it has n zeros. And parenthetically, some of those zeros, they may be repeated. That is, there could be multiplicity. So think about what this is saying. If you have a polynomial of degree 5, you know there has to be 5 zeros. Some of them may be repeated, but you have to have a total of 5 zeros. So let's try an example. try to put this all together into an example. I'm going to erase this because I want to have plenty of space, plenty of room for this example, and show you how I kind of bring everything that we've seen so far this week, kind of bring it all together. So this example, say we're going to find all complex zeros of the polynomial function x to the fourth minus 6x cubed plus a 10x squared plus 2x minus 15. The first thing that I note, the degree of this polynomial is 4. So we have to have 4 complex zeros. We have to have 4 total complex zeros. Now some of them may be repeated, but we know there are 4 because the degree is 4. Here's how I would attack the problem. The first thing I would do is list all possible rational zeros. So that's kind of like the example, the last example we did. We listed all the possible rational zeros. So to list all the possible rational zeros, first, the possible rational zeros. Well, remember we got to write down the factors of P and the factors of Q. Remember, P will be the factors of the constant term. So it's plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. The factors of Q, well, that's going to be pretty friendly. Factors of Q, those are the factors of the leading coefficient. The leading coefficient is 1. So that's it for the factors of Q. So our possible rational zeros, the possible rational zeros are plus or minus 1 over plus or minus 1, plus or minus 3 over plus or minus 1, plus or minus 5 over plus or minus 1, and plus or minus 15 over plus or minus 1. So right now we have our list of possible rational zeros. And what I will do next, the second thing I do, is I use my graphing calculator, and I'm going to graph the polynomial function. So let me make a note here. I'm going to graph it. And by looking at my possible rational zeros, that's going to tell me my viewing window to graph the function in. It's going to tell me specifically what my x-min and my x-max should be. The smallest number I see here is, well, negative 15. So I would, I'll make my x-min negative 20. The largest number I see is 15. So I'll make my x-max positive 20. And I'll end up scaling my x-axis by 4s. For the y-axis, I'm going to have a y-min of negative 10. I'll do a y-max of 10. And I will scale my y-axis by 1s. So what I'm going to do right now is I'm going to get my graphing calculator. I'm going to graph this function in this viewing window and show you how I would proceed from there.
All right, hey folks, here we are at the point in the problem where I said we should take a look at the graph. So there was our function, x to the fourth minus 6x cubed plus a 10x squared plus 2x minus 15. Keep in mind the possible rational zeros are plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. So here we go. We're going to look at the graph. So let me enter this into my calculator. So that's an x to the fourth minus a 6x cubed. And then it's plus 10x squared. So there's 10x squared plus a 2x minus 15. Now I told you what I would do here is I would make my viewing window negative 20 on the x-min to 20 for the x-max. And remember, that's because my smallest possible rational 0 is negative 15, and the largest is positive 15. And I'll scale by 4s. And it looks like my y min, I said, would be negative 10, my y max 10, scale by 1. So that all looks good. So here I go. I'm going to hit graph. So when I hit graph, here comes the graph. Oh, it's taken a while, but there it is. Okay, now when I look at it, it's like, oh, geez, I see there are two x-intercepts there. And from my guesstimation, because I scaled, keep in mind, I scaled my x-axis by 4s, it looks to me like this x-intercept right here, it looks like that's possibly a negative 1. So it looks like it might be a negative 1. So here's how I'm going to see if it is negative 1. I am going to use the power of the remainder theorem. In other words, if I evaluate my function at negative 1 and I get a result of 0, then I know negative 1 is a 0. So let's, let me do a little calculate here real quick. Let me do number 1, value at x is negative 1, and let's see what comes out for y. Y, look at that. X is negative 1, y is 0. That tells me negative 1 is a 0. Since I scaled my x-axis by 4s, I'm going to guess that this x-intercept right there, I'm going to guess that is positive 3. So let me use the power of the remainder theorem, and let me second that. Let me do the value of x is 3. And check it out. Out came a y value of 0. So that tells me at this point in time, when I put 3 in for x, out came 0. When I put negative 1 in for x, out came 0. So at this point in time, I know negative 1 is a 0, and I know x equals 3 is a 0. So right now, the two zeros I know are x equals negative 1 and x equals 3. Now let's see what we can do with that information.
Okay, now that we've looked at the graph, and what the graph showed us was that the graph along with the remainder theorem, factor theorem, showed us that 3, x equals 3, and x equals 1, or negative 1, were the rational zeros that are in our list. So from the graph, we know that x equals 3 and x equals negative 1 are zeros. Our factor theorem tells us that if x equals 3 is a 0, thanks to the factor theorem, we know x minus 3 is a factor. Since x equals negative 1 is a 0, we know x plus 1 is a factor. Okay, now see where we're going to go with this. If we know a factor, we should be able to, factor this beastie down. Here's how I'm going to do it. I'm going to take this and I'm going to crank it through synthetic division. I'm going to take this polynomial, so let me write down the coefficients. 1, negative 6, 10, 2, and negative 15. And I'm going to crank it through synthetic division. Give myself a little more space here. I'm going to crank it through synthetic division, and I'm going to start with this one first, the x minus 3. The x minus 3, we know that's a factor, so we're going to synthetically divide the polynomial by x minus 3. So you remember the process of synthetic division? I'll put the 3 out here, bring the 1 on down. 3 times 1 is 3. Add, so that gives me a negative 3. 3 times negative 3 is negative 9. Add them together, so that's 1. 3 times 1 is 3. Add them together, so that's 5. 3 times 5 is 15. Add them together, we get 0. It's not a surprise we get 0. That's the remainder. Since it's a factor, we have to get a remainder of 0. And at this point in time, Let's do a little progress check. At this point in time, we know that our original function, x to the fourth minus 6x cubed plus 10x squared plus 2x minus 15, we know that it factors to x minus 3 times, and that's the quotient. So that's an x cubed minus 3x squared plus x plus 5. So that's like a progress check. What do I do next? What I'm going to do next is I'm going to take this beastie here and I'm going to do synthetic division with x plus 1. Because I know x plus 1 is a factor of the original polynomial. It has to appear in here as a factor. So it's a factor of this x cubed minus 3x squared plus x plus 5. So if I, well, let me do a little erasing here because I've run out of room. So if I continue and I take the x cubed minus 3x squared plus x plus 5 and divide it by x plus 1, I'm going to do synthetic division on it. I'll write down the coefficients. 1, negative 3, 1, 5. Oops, didn't leave myself enough room. I'm going to synthetically divide that by x plus 1. So that means I need to put a negative 1 here. And let's go through the process of synthetic division. Bring the 1 on down. Negative 1 times 1, negative 1. Add them. Negative 4. Negative 4 times negative 1 times negative 4 is 4. Add them. Gives me a 5. Negative 1 times 5 is negative 5, and absolutely no surprise, the remainder is 0, because we knew it was a factor. So what does that mean? That means our original function, that x to the fourth minus 6x cubed plus 10x squared plus 2x minus 15, it means we now know that it factors to x minus 3 times x plus 1 times x squared minus 4x plus 5. The original question was find all the complex zeros. Well, we have the 0 here, x is 3. We have the 0 from this factor, x is negative 1. The other zeros are found by taking that quadratic equation and setting it equal to 0 and solving. If we set it equal to 0, and solve that equation, it's not going to factor. You're going to have to use the quadratic formula on this. And I'm going to save the work of the quadratic formula to you. I think you know how to use the quadratic formula. But here's what you're going to get. You're going to end up getting x equals 2 plus or minus I. So let's answer the question. The question, what are all the complex zeros? So the answer, the complex zeros are x is negative 3, x is positive 3, x is negative 1, x is 2 plus I, and x is 2 minus I. 4 zeros. There are 4 total zeros there. That's how many we expected to see, were 4 total zeros. 1, 2, 3, 4. You could even write that original polynomial in completely factored form as long as you use these complex coefficients. Before I wrap this up, any polynomial function that you can think of with real coefficients can eventually get factored down to nothing but linear factors and quadratic factors. And then if you allow complex coefficients, like the 2 plus I and 2 minus I, you could actually write that original polynomial as a product of 4 linear factors. X minus 3, x plus 1, x minus the quantity 2 plus I, and x minus the quantity 2 minus I. But that's how I would attack one of these problems of finding all the zeros. It's kind of brought everything into play. Our rational zeros theorem, listing the possible rational zeros, looking at the graph, using the remainder theorem to verify what the graph is telling us, synthetic division, factor theorem, and even a little quadratic formula at the end. So it brings together a lot of stuff into one problem. And that's it for that example. Hey, if you look back at that last example, we ended up with 2 complex zeros in there in our final answer, 2 plus I and 2 minus I. That kind of leads into the next theorem, which is called complex conjugate pairs. And basically it just says that if A plus BI is a 0, then A minus BI must also be a 0. That's complex zeros don't just appear as single entities. You can only have an even number of them. They have to come in pairs. So if you know 3 plus 4i is a 0, then 3 minus 4i must also be a 0. Let me show you how to do one of these. You'll see some of these problems in the homework, just using that information. So let's say you're asked to find a polynomial function. So find a polynomial function. And let's say it has a degree of 3. And you're told it has zeros of 2 minus 5i and negative 4. That's all you're given. You're supposed to come up with the polynomial function. The first thing that I would note is that if 2 minus 5i is a 0, then the complex conjugate pairs theorem says 2 plus 5i must also be a 0. And then negative 4 is a 0. So if you have a degree 3, we have 3 zeros. If you have zeros, then you have to know what the factors are. That's the factor theorem. So since we know these are zeros, that would correspond with the following factors: x minus 2 minus 5i, x minus 2 plus 5i, and x minus a negative 4, which we'll end up writing that as x plus 4. Since we have the factors, all we have to do is multiply these factors together to get the original polynomial function, to get the third degree polynomial function. So if we bring the factors on over here, draw a little line down, we're going to take the factors x minus 2 minus 5i times x minus 2 plus 5i times x plus 4. So we're going to take these factors and multiply them together, and the hardest part here is just taking your time. It's kind of tedious, it's kind of laborious, but I would put in an extra step. X minus the 2 minus 5i, I would write that as x minus 2 plus a 5i. X minus 2 plus 5i, I would write that as x minus 2 minus 5i. And x plus 4 I'll write as x plus 4. Okay, now I'm going to do it a step at a time. I'm going to take this mess here and multiply it by this mess here. It's an advanced form of, it's just foiling them, but I'm extending the foiling concept. So here we go. X times x is x squared. X times negative 2, negative 2x. X times negative 5i is a negative 5ix. Now I take the negative 2 times x. That's a negative 2x. Negative 2 times negative 2 is a plus 4. Negative 2 times negative 5i, well, that's a plus 10i. And I'm not done. 5i times x, that's a 5ix. 5i times negative 2 is a negative 10i. And then 5i times negative 5i, that's a negative 25i squared. Just barely got that on the board. Now keep in mind, this mess then gets multiplied by x plus 4. Holy moly. But look, some neat things happen here. Let's combine some like terms. First off, x squared. Well, there's nothing like x squared, so let me bring that on down. I've taken care of that. We have a negative 2x. Here's another negative 2x. Okay, I don't see any other x's, so negative 2x minus 2x, that's a negative 4x. So I've combined all the just real coefficient x terms. Negative 5ix, and oh hey, look, here's a 5ix. They cancel out. Sweet. Look, a 10i and minus 10i, they cancel out. That's nice. So we're just left with plus 4, and then we have this minus 25i squared. But wait a minute, what's I squared? Well, I squared is negative 1. So this minus 25, I'm going to replace I squared with a negative 1. That would give me a plus 25. And like I said, don't forget the x plus 4 factor. So really I have an x squared minus 4x plus a 29 times an x plus 4. And again, I'm just going to multiply this out. X squared times x is x cubed. X squared times 4 is a 4x squared. Negative 4x times x. Well, look at that. That's a negative 4x squared. Negative 4x times 4 is a minus 16x. Then finally we have a plus 29x. Plus 29 times 4. 29 times 4 is 116. Combine like terms and you end up with an x cubed. The x squareds cancel. Plus 13x plus 116. It's not a difficult problem. It's just long, it's kind of tedious, and take your time. The most difficult part is probably keeping track of this being multiplied by that. That's why I decided to show it to you step by step, and how I take the first term and I distribute it to each term here, write them down. Then I come back and pick up this, distribute it to each term here. Just take your time and be neat, and hopefully you'll persevere on it. But that's it for that example. Okay, the final topic you'll see this week deals with rational functions. You'll see in the ebook the definition of a rational function. Basically a rational function, it looks like a fraction, but it's going to have the form of being a polynomial function over a polynomial function. So let's look at this rational function I've written down. Here's an old question. What is the domain? And remember, the domain is going to be all reals except those values of x that would make the denominator equal to 0. So let's look and see what makes the denominator equal to 0. Hopefully this factors. And let's see, I think it does. Yep. So these are the two values of x that would make the denominator 0. They're not in the domain. So in interval notation, the domain would be negative infinity to negative 6, union with negative 6 up to 2, union with 2 to infinity. So it's all real numbers except -6 and except 2. So that's a real old question. Okay, continuing on with rational functions. You're going to start looking at the graphs of rational functions, and one thing that's going to match up with the domain, kind of like the last example we did, is those values of x that are kicked out of the domain, that are not in the domain, those values of x that makes the denominator 0. Graphically, that's going to produce either a vertical asymptote, which is a vertical dashed line that the graph will not cross, or there'll be a hole in the graph. So I'm going to show you how you can tell whether or not it's going to be a vertical asymptote or a hole in the graph. And it's really this straightforward. Look at the denominator. Find the values of x that makes the denominator 0. So here, find the values of x that makes this denominator 0. Well, this denominator factor is very friendly. You have 2 values of x that makes the denominator 0. So just a review, that tells me the domain is -∞ to -3, union with -3 to -1, union with -1 to infinity. But now I'm going to ask the question about these excluded domain values. -3, it's not in the domain. -1, it's not in the domain. Would the graph of this function have a vertical asymptote or a hole in the graph? And here's how you can tell. For these values of x that makes the denominator 0, see what it does to the numerator. In other words, this value of x makes the denominator 0. But if you take this value of x that makes the denominator 0 and toss it into the numerator, you get -2. If a value of x that makes the denominator 0 produces a non-zero number in the numerator, that is going to produce graphically a vertical asymptote. Here's a value of x that makes the denominator 0. But this value of x also makes the numerator 0. A value of x that makes the denominator 0, if it also makes the numerator 0, that's going to produce a hole in the graph. So short and sweet. Find values of x that makes the denominator 0. That's an old question, really. It's the domain. Those values of x that makes the denominator 0 is either going to graphically produce a vertical asymptote or a hole in the graph. If a value of x that makes the denominator 0 makes the numerator not 0, you have a vertical asymptote. If the value of x that makes the denominator 0 also makes the numerator 0, you have a hole in the graph. Now I'm going to leave, that's where I'm going to end this. There's going to be something you're going to read about horizontal asymptotes, and then you're going to put it all together and making graphs. But I just wanted to hit some of the high points for rational functions. When you look at the horizontal asymptote stuff, keep in mind what's important there will be degree of the numerator, comparing it to the degree of the denominator. And that will tell you a lot of stuff about horizontal asymptote. But that's it. It's kind of the high points of what you're going to be studying this week in week 9 in this online college algebra class. Thanks for watching.